Good morning. This is Dr. Padma, Assistant Professor, Department of Physics, Institute of Aeronautical Engineering, Hyderabad. In previous session, we discussed about the fundamentals of semiconductor devices. Those are semiconductors, what is semiconductor, types of semiconductors, like that. Today's session, we will discuss about the carrier concentration and Fermi level in intrinsic semiconductors. Carrier concentration in intrinsic semiconductor. When a suitable form of energy is supplied to a semiconductor, then electrons take a transition from valence band to conduction band. So, for example, this is conduction band and this is valence band. If a suitable form of energy is supplied to any semiconductor, then the electrons take a transition from valence band to conduction band. If a suitable energy is supplied to any semiconductor, then the electrons take a transition from valence band to conduction band. Hence, a free electron in conduction band and simultaneously a free hole in valence band is formed. For example, if a suitable energy is supplied to any semiconductor, an electron take a transition from valence band to conduction band. It creates a hole in the valence band and it takes a transition from valence band to conduction band. Here, conduction electron is there. So, free electron in conduction band and simultaneously a free hole in the valence band is formed. This phenomena is known as the electron-hole pair generation. So, when a suitable energy is supplied to any semiconductor, then an electron takes a transition from valence band to conduction band. It creates a hole in the valence band. Simultaneously, a free conduction electron and a free valence electron is created. This phenomena is known as the electron-hole pair generation. In intrinsic semiconductor, number of conduction electrons will be equal to number of vacant sites, which is also known as the holes in the valence band. So, in intrinsic semiconductor, the concentration of electrons will be equal to number of holes. Calculation of density of electrons. Let Dn be the number of electrons available in between the energy level E and E plus dE. Let us take Dn is the number of electrons which are available in between the energy levels of E and E plus dE in the conduction band. So, let Dn be the number of electrons. Dn can be derived as Dn equal to Z of E dE into F of E, where n equal to integral EC, conduction band starting from bottom of the conduction band to top of the band, Z of E, F of E dE. This is equation 1. Where Z of E dE is the density of states in the energy interval E and E plus dE, and F of E is the probability of the electron occupancy. So, n equal to integral EC to top of the band, Z of E, F of E dE, where Z of E dE is the density of states in the energy interval E and E plus dE, and F of E is the probability of the electron occupancy. We know that density of states, that is the number of energy states per unit volume, is known as the density of states. Density of states means the number of energy states per unit volume within the energy interval E and E plus dE is given by Z of E dE equal to 4 pi by h cube 2m whole to the power of 3 by 2 e power half into dE. So, Z of E dE equal to, here we can calculating the density of electrons. That's why we are replacing m with me. Me is the mass of the electron. Z of E dE equal to 4 pi by h cube 2 me star whole power 3 by 2 e power half into dE, where me is the effective mass of the electron. So, since E states at the bottom of the conduction band EC, Z of E dE equal to 4 pi by h cube 2 me star whole power 3 by 2 E minus EC whole power half into dE. Here E starts from the bottom of the conduction band to EC. probability of an electron occupying in the energy state E is given by probability of electron occupying is denoted as f of E. F of E equal to 1 by 1 plus exponential of E minus EF by kT. For all possible temperatures, E minus EF value should be greater than kT. Then equation can be written as f of E equal to 1 by exponential of E minus EF by kT. F of E equal to exponential of minus E minus EF by kT equal to exponential of EF minus E by kT. So here exponential of minus E minus EF by kT can be written as exponential of EF minus E by kT. So substitute the values of f of E and z of E values in equation 1. We will get the number of electrons. Here n is the number of electrons presented in the conduction band. That is integral EC to top of the band z of E, f of E, dE. Here we are substituting the values of z of E and f of E values in this equation. We will get the equation n equal to integral EC to infinity 4 pi by h cube 2 me star whole power 3 by 2 e minus ec whole to the power of exponential of ef minus e by kt into de. So here this equation can be written as n equal to 4 pi by h cube 2 me star whole power 3 by 2 is the constant value. Integral ec to the infinity e minus ec whole to the power of exponential of ef minus ea by kt de. So n equal to 4 pi by h cube 2 me star exponential of ef by kt integral ec to infinity e minus ec whole to the power of exponential of minus e by kt into d. This is the written as equation 2. So to solve the equation 2, let us put e minus ec value as x. Let us assume that e minus ec value should be x. E equal to ec plus x, where de equal to dx. Then equation can be written as n equal to 4 pi by h cube 2 me star whole power 3 by 2 exponential of ef by kt integral 0 to infinity e minus ec whole to the power of exponential of minus e by kt into d. Now n equal to 4 pi by h cube 2 me star whole power 3 by 2 exponential of ef by kt integral 0 to infinity. In the place of e minus ec we can write as x to the power of half exponential of e value is ec plus x. So in the place of e we can written as ec plus x by kt into dx. N equal to 4 pi by h cube 2 me star whole power 3 by 2 exponential of ef minus ec by kt. This is written as ef minus ec by kt integral g. These are all the constants. Integral 0 to infinity x power half exponential of minus x by kt into dx. This is equation 3. We know that by solving the equation 3, we will get the value of integral 0 to infinity x power half exponential of minus x by kt into d equal to kt whole to the power of 3 by 2 pi power half by 2. Substitute in equation 3 in this value of integral 0 to infinity x power half exponential of minus x by kt d equal to kt power 3 by 2 pi to the power of half by 2 value in equation 3. We got the concentration of electrons n equal to 4 pi by h cube 2 me star whole power 3 by 2 exponential of ef minus ec by kt whole to the power of 3 by 2 pi to the power of half by 2. By solving this equation, we got the value n equal to 2 into 2 pi ma star kt by h square whole power 3 by 2 into exponential of ef minus ec by kt. The above equation represents the number of electrons per unit volume of the material. This is the equation for number of electrons present per unit volume of the material. This is known as the carrier concentration of electrons. Similarly, we can derive the equation for number of charge carriers of holes P equal to similarly 2 into 2 pi mh star kt by h square whole to the power of 3 by 2 exponential of EV minus EF by kt. Here mh star is the mh star is the effective mass of holes. So in the place of Me star, we can replace Mh star. Why? Because here we are solving the equation for the number of holes per unit volume. So the number of holes per unit volume P equal to 2 into 2 pi Mh star Kt by h square whole to the power of 3 by 2 exponential of EV minus EF by Kt. This equation represents the number of holes per unit volume of the material. Now in intrinsic carrier concentration, in intrinsic semiconductor, the number of holes is equal to number of electrons. N equal to P. Number of electrons will be equal to number of holes. Hence N equal to P equal to N is called the intrinsic carrier concentration. So in intrinsic semiconductors, the number of electrons will be equal to number of holes. That's why we can written as N equal to P equal to N in intrinsic carrier concentration. So that Ni square equal to N into P. Ni square equal to N into P. Ni equal to under root of Np. So Ni value should be, what is the N value here? Here N value is 2 into 2 pi Me star Kt by h square whole power 3 by 2 exponential of EF minus EC by Kt, whereas P value should be 2 into 2 pi mh star Kt by h square whole power 3 by 2 exponential of EV minus EF by Kt. Here this value is equal to N, this value is equal to P. We are substituting N and P values in this equation. Then we will get Ni value is 2 into 2 pi Kt by h square whole power 3 by 2 into Me star mh star whole power 3 by 4 exponential of EV minus EC by 2 Kt. Ni equal to 2 into 2 pi Kt by h square Me star mh star whole power 3 by 2 exponential of minus Ec by 2 Kt. Here Ec equal to energy gap, that equal to Ec minus Ev. So here Ev minus Ec means minus Ec. So in the place of Ev minus Ec, we are writing minus Ec. So next, Fermi level in intrinsic semiconductor. Already we know that in intrinsic semiconductors, the number of holes N equal to number of electrons N equal to number of holes P. Then what is the N value? Here we got N value is 2 into 2 pi Me star Kt by h square whole power 3 by 2 into exponential of EF minus EC by Kt, that equal to 2 into 2 pi mh star Kt by h square whole power 3 by 2 into exponential of Ev minus Ef by Kt. This is the P value. We are equating N equal to P. Why? Because in intrinsic semiconductors, the number of electrons will be equal to number of holes. From this equation, 2 pi Me star Kt by h square whole power 3 by 2 exponential of Ef minus Ec by Kt equal to 2 pi mh star Kt by h square whole power 3 by 2 exponential of Ev minus Ef by Kt. From this equation, exponential of 2 Ef by Kt equal to mh star by Me star whole power 3 by 2 exponential of Ev plus Ec by Kt. Taking logarithm on both sides, we got the value Ef equal to 3 Kt by 4 log of mh star by Me star plus EV plus EC by 2. In intrinsic semiconductor, we know that effective mass of electron is equal to effective mass of hole. From this equation, this term will be 0. Log 1 will be mh star by me star means log 1. Log 1 will be 0. So this term total will be 0. Then we got the value finally EF equal to EV plus EC by 2. Thus, the Fermi energy level EF is located in the middle of the forbidden band. So, this is the energy band diagram for intrinsic semiconductor. Here, we are observed that the above band is the conduction band and bottom band is the valence band. Here, we observe that the Fermi level lies in between the conduction band and valence band. Why? Because here the number of electrons in the conduction band is equal to number of holes in the valence band. So, in intrinsic semiconductors, the Fermi level lies in between the conduction band and valence band, in the middle of the conduction band and valence band. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.